class 每个你就那 class 每个人。Oh, come on. Ouch, man. Yes. Okay, I will begin my class now. So, in the last online lecture, we have introduced a new physical quantity, a new mathematical concept, actually, a new mathematical concept of describing a physical quantity. So, as I already said, there are certain physical quantities beyond this tensor and vector classification. There are certain physical quantities or engineering quantities that cannot be expressed mathematically, and they are beyond the concept of this vector and scalar notation as we know it. So the example that we discussed was the conductivity tensor. So in the case of anisotropic crystals, there is a like interdependency. So in isotropic crystals, like the simple relation here, the conductivity is a scalar quantity. The conductivity is a scalar quantity, and in such isotropic crystal, if you have electric field along x direction, you will have electrical current density Jx or electrical current along that direction. But mute Maria. Maria Rojami. Sorry, yeah, now it's muted. So when we have isotropic crystals, we have current which is directly proportional to electric field. If you have electric field in x direction, you have current in x direction. And if you have electric field only like this, if you have electric field only in x direction, you do not have any current along y, you do not have any current along z. So the current along y and z will be zero in such isotropic crystals, isotropic material. Apply electric field in one particular direction, there will be a corresponding current or charge transfer or charge flow in that direction only in isotropic crystals. So in such simple isotropic crystals, the relation between current density and electric field is with a proportionality constant of a scalar quantity called sigma, which is called your scalar conductivity. But in anisotropic crystals, if you apply electric field along x direction, which you can denote it as Ex, or you can denote it as E1. If you apply electric field along x direction, not only that, you will have current along x direction, which you can write it as J1. you will also have a current along y direction, current along z direction. So the electric field applied in one particular direction may influence the current flow along other directions also. So in such anisotropic crystals, you no longer have a simple relation between electric field and sigma with a proportionality constant. A simple relation between electric field and current density with a proportionality constant of sigma. So this sigma, the conductivity, is now what we now term it as a tensor. What we now term it as a tensor, and we will continue our discussion along that line to represent such physical quantities, such physical concept using this tensor mathematics. So tensor will be another way of representing, analyzing, way of representing a physical system or engineering system. So let us start with what we are familiar with, called coordinate transformation. Now, if I have a point P here, the point P, the point P here will have a coordinate value of x and y here. If you define the location of this point P with this x, y coordinate system, in order to know the location of the point P, what you have to know is the x coordinate value and the y coordinate value. So once you know the x coordinate value and the y coordinate value, the point P location is defined. Now, in that same space, if I define another coordinate system called x prime, y prime coordinate system. So if I define another coordinate system called as denoted here as x prime, y prime coordinate system, here you see that the prime coordinates is slightly shifted or slightly rotated by an angle of theta here. The prime coordinate is slightly rotated by an angle of theta, but they both have the same origin. They both maintain the same origin here. They both have the same origin, but only the difference only between these two coordinates is that the prime coordinate is slightly rotated by an angle of theta. Now, in order to identify the location of the same point here, in the prime coordinate, in order to identify that, I have to know what is the corresponding coordinate value along x prime, the corresponding coordinate value along y prime. So I need to know this. So I can define the location of the same point if I define the distance along this x prime, that is between this and this, and the height in the prime coordinate is this to this. This is the height in the prime coordinate if I define this. That is your y prime. So using x prime, y prime in the prime coordinates, using xy in the unprime coordinates, I can define the location of the same particular point. Now, I can write the relation between these two coordinate system. How do I write the relation between this coordinate system? From the figure, you can see that x prime is equal to x cos theta plus y sin theta. Now let us just see x cos theta plus y sin theta, right? So this is your x prime. Now can you write x? Now let us try to write down x prime in terms of x and y coordinate. This is x prime and this is x. So if this between this to this is x, then if you drop a perpendicular here, so this is theta, means that this length between this to this length will be your x cos theta. This is theta here. If you see the trigonometry here, this is a right angle triangle here, dropping a perpendicular to this x prime coordinates from this point to this, you will have 90-degree here. This is a right angle triangle with theta here. So if this length between these 2 points is x, then the distance between this and this will be x cos theta. Now, what is your y here? Your y here is this. From this to this is your y. This to this is your y. Now, you can imagine you can imagine another line here. Let me put a dotted line here. So here this is theta, means from geometry this is also theta, and from geometry this angle and this angle are equal, they are alternate angles, so this angle is theta, and if you continue the line here you can see that this is 90 degree. So between this point and this point, you can imagine there is another right angle triangle. So if this is theta, means what is this length here? This length, if you look at this geometry here, this length will be from trigonometry, from this point to this point. If this point P to this is y, if this is y here, this is y here, then this point to this point will be y sine theta. So as you see, your x prime, which is from this to this, will be addition of this and this. The addition of this two segment of line will give you your x prime. So this segment of line in terms of x is x cos theta, and this segment of line here in terms of y is y sine theta. You can just see from the figure. Just try to picture a right angle triangle over here as I draw in the with the dotted line and all. Now, how do I write our y prime now? Y prime is this. Now, in order to get y prime here, if you look at this, this is your y prime. If you look at this, what is the distance between this point and this point? What is the distance between this point and this point? That is this. What is this distance here? This to this. If you look at this, the distance between these 2 points in terms of theta and x will be, you will see that this is your x sine theta, isn't it? This is a right angle triangle, so this is theta, this base, this hypotenuse is x here, so this will be x sine theta. And what is this whole length from this point to this point, this whole length will be, if you look at this whole length from this to this will be same as the distance of this to this. So that will be your y cos theta. This is your theta here, this is your y, and this to this will be your y cos theta. Now what is your y prime? Y prime is between these 2 points. Y prime is between this. So y prime will be y cos theta minus x sine theta. Okay, y prime will be y cos theta minus x sine theta, which you can write as minus of x sine theta plus y cos theta. Right, just like this. So this relates the coordinates in the prime coordinates, x prime and y prime. This is called prime coordinates. This relates the coordinate variables in the prime coordinates with unprimed coordinates variables. Unprimed coordinates. So prime means you are putting a hyphen here. Okay, you are putting a hyphen here. Prime coordinates, the hyphen coordinates, and this is the unprimed coordinates. X, Y are the coordinate variables in unprimed coordinates. In the prime coordinates, you have x prime, y prime. So x prime, y prime, and x, y, they are the two coordinate system defining the location of a point P, same point in the same space, but one coordinate system is rotated or slightly shifted from another coordinate system, but they do have the same origin at the same point here. They have the same origin here. So in this way we can relate the coordinate variables in prime coordinates with the coordinate variables in prime coordinates. And this above set of linear equations can also be written like this. You can just simply write it like this. J equal to, in terms of indices, you can write it like this. J equal to 1 means corresponding to J equal to 1. Sorry, corresponding to, let's say, I equal to 1. I equal to 1 means x1 prime. I equal to 1 means x1 prime. And J is summation from 1 to 2. J is summation from 1 to 2 means I is 1 here, A1, J is 1, X is 1, plus I is 1 here, I1. Now J is 2 in the next term, 2, J is 2, X2. So for I equal to 1, this will give me x1 prime equal to a11 x1 plus a12 x2. Now you consider I equal to 2 here. If you consider I equal to 2, instead of I here you put 2, you will get x2 prime. Instead of I you put 2, x2 prime. Instead of I we already have 2, so a2. Now you start the summation from j equal to 1 to 2. J is 1, a2 1, j is 1 plus a, I is already 2 here, a2, j is 2, x is 2, a2 2, x2. So you can have a set of linear equations. You can represent it like this. And here in our notation here, new notation, we using indices, x1 is simply equal to x, x2 is simply equals to y, and your x1 prime is simply x prime, your x2 prime is simply your y prime. Okay, if you compare with this. And your a11 is cos theta, a12 is sine theta, a12 is sine theta, and a21 is minus of sine theta, a22 is this cos theta. Okay, so like that we can write this as this. Okay, so aij is simply defined like this. Aij is defined using this directional cosines. A11 is, as I was looking like from the comparison with this and this, I was like just explaining here that a11 is cos theta, a12 is sine theta, a21 is minus sine theta, a22 is cos theta, and these are called directional cosines. Okay, directional cosines. So this is actually, if you look at this, what was our x1? X1 prime was, if you remember what I was writing, a11 x1 plus a12 x2. Now you differentiate this x1 prime with respect to x1. If you differentiate that, a11 is constant, del x1 upon del x1 plus a12 del x2 upon del x1. So x1 and x2 are coordinate variables. Differentiation of one coordinate with respect to x, this is same as x2 is y, as I just explained here. X2 is like without indices, you can represent it as xyz. With indices, I represent it as x1, x2, x3. Yeah. So del y upon, it's like del y upon del x, which is 0. Okay. So this is like the first term is like del x upon del x. This is 1. So this will be a11. So a11, as you see, a11 as you see this del x1 prime upon del x1. A12 is del x1 prime upon del x2, and similarly a21 is del x2 upon del x1. So here instead of writing our coordinate system as x, y, z, in tensor notation, we will instead use indices notation x1, x2, x3. So instead of prime coordinates like x prime, y prime, and z prime, we will often use a notation called x1 prime, x2 prime, x3 prime. Okay. So similar to what I've just explained here, if you take the differentiation of del of x1 prime with respect to del of x2, this will be a11 del x1 upon del x2 plus a12 del x2 upon del x2. This will be again 0, so this and this will be cancel out. a12 is equal to del x1 upon del x1 prime upon del x2. Okay, so this you can write. So this transformation relations, which we write it like this, we can now write it as this. Aij, we can simply write it as, if you look at this, a11 is del x1 del x1 prime del x1, a12 is del x1 prime del x2, a21 is del x2 prime del x1, a22 is del x2 upon del x2, del x2 upon del x2 prime upon del x2. So you can write the above set of relations. You can combine it using this single relation that is called aij is equal to del xi prime upon del xj. Okay, so this simply means that if I is 1, j is 1, then you have a11, that is del x1 prime del x1. If I is 1, j is 2, then you have, instead of aij, I is 1, j is 2, a12 equals to del x1 prime upon del x2. So likewise, you can write I equal to 2, j equal to 1 will lead to a21 del x2 prime del x1. So like that, you can represent this coefficient, this what are aij actually? Aij are the transformation coefficient. This is a transformation relation between the coordinates of the prime and unprimed. Aij is the transformation coefficient. The transformation coefficient can be written as this partial derivative. The transformation coefficient can be written as a partial derivative. Okay, so from here, by writing aij as del x I prime upon del xj, del xi prime upon del xj, you can rewrite this. So this is the transformation, the relation between the coordinates in the unprimed and the coordinates in the primed. So the coordinates in the unprimed and the coordinates in the coordinates in the primed and the coordinates in the unprimed, they are having this transformation relation, and the transformation relation, the coefficient of transformation relation is del x prime del xi prime upon del xj, del xi prime upon del xj. Okay, so this is what we should remember for now. Now let us move forward to what is defined as chronicle delta. Chronicle delta is simply, we know that as I have just said here before, what is that? Yeah, we, instead of x, we use in tensor notation, in tensor algebra, instead of x we will write x1, instead of y we will write x2, instead of z we will write x3 in tensor algebra. So when we write del xi upon del xj if I equals to j, if I and j are equal. That means if I equal to 1, j is also 1. Then in that case, what we get here is del x1 upon del x1. Del x1 upon del x1 is as good as writing del x upon del x. This is 1. Now, if I equal to true, if I and j are equal, if I equal to true, j will also be true. Then this will be del x true upon del x true. What is x true here? In terms of our familiar Cartesian system, x true is y. So del is good as writing del y upon del y, which is 1. Now, if I does not equal j here, if I does not equal j, now consider I equal to 1. Let us take another j value other than 1, that is 2, for example. Then this ratio del xi upon del xj will now become del x1 upon del x, instead of j it is 2, del x1 upon del x2. What is x1? x1 is x, del x. What is x2? x2 is y, del y. So differentiation of one coordinate variable with respect to another coordinate variable will be 0. Right. So you can consider another case also. If you consider I equal to 2, let's say j is some other index value other than I, that is I value is 2. If I is not equal to j, then j, let us consider 1, take it as 1. Then this will be del x 2 upon del x. You just put I as 2 here, j as 1 here, del x2 upon del x1. So what is x2 here? x2 is y, del y upon, what is x1? x1 is simply x in our familiar core Cartesian system. So del y upon del x is differentiation of one coordinate variable with another coordinate variable. This will be 0. So all in all, you will see that this quantity, that is del xi upon del xj, will be equal to 1 if I is equal to j. If I does not equal j, this quantity will be 0. Okay. If I equal to 1 here in this partial derivative, sorry, if I equal to j, then this quantity is 1. Whether I is 1 or not, I is 1 or I is 2, as long as I and j are equal, this del xi upon del xj equals 1. As long as I does not equal j, then del xi upon del xj will be 0. So this quantity is known as Kronecker delta function. In tensor algebra, we call it a Kronecker delta function. Okay. So this quantity can be represented using two indices here, I index and j index. So let us write as sigma ij, sigma ij. So in the sigma ij, if I is equal to j, it is always 1. If I does not equal j, it is 0. So that is a simple definition of Kronecker delta. Now, so I don't want to cover a lot of topic because tensor is something like like new mathematical concept, new mathematical formulation, which you are not yet familiar. So I will not cover a lot of topic tonight, today. So what are scalars? Transformation of scalars. Let us look at scalar quantities. Scalar quantities are physical quantities which are only having magnitude, only without any direction, such as mass, temperature, energy, etc. Now, let us consider at this point, suppose you measure the temperature at this point. Suppose you measure temperature at this point, and suppose you are in x, y coordinate system, unprimed coordinate system. You measure temperature at this point, and you find that temperature at this point is 26 degrees Celsius. Now, let us consider another coordinate system, our x prime y prime coordinate system, another coordinate system in the same three-dimensional space. If you consider another coordinate system with the same origin here, measure temperature at this point from your location in this coordinate x prime y prime coordinate. Do you think the temperature at this point will change? It will not change, isn't it? So this temperature, as you see, at this particular point, it is measuring the amplitude only, or it is having amplitude only. Temperature is a physical quantity that only has a magnitude. So not amplitude, that only has a magnitude. Okay, so it has a magnitude. How hot it is at this particular point can be measured using your thermometer at this point, that is 26 degrees Celsius. If you are in your xy coordinate and prime coordinate, even if you measure from another coordinate, the temperature at this same location will still be 26 degrees Celsius. So it is irrelevant whether you measure it from prime coordinate, that is x prime, y prime coordinate, or unprime coordinate, xy coordinate. So similarly, the mass of any object also is a scalar quantity. Whether you measure it from primed or unprimed, you will get the same value. You will get the same value, isn't it? So therefore, we see that if I have any physical quantities that are scalars, then under the coordinate transformation from prime to unprimed, the physical quantity does not change. The physical quantity does not change under coordinate transformation if that physical quantity is a scalar quantity. So therefore we see that scalars are invariant. Scalars are invariant to coordinate transformation. Coordinate transformation. Even if you have a coordinate transformation, scalar quantities will not change. Scalars are invariant to coordinate transformation. Okay, so therefore a prime, let's say a prime is the temperature we measured from the prime coordinate. If a is the temperature value we measure from the unprime coordinate, in both the cases the temperature will be measured as 26 degrees Celsius each. That is, a prime will be equal to a. So whether you measure it in the primed or unprimed, you are still getting the same amount of value if a physical quantity is a scalar quantity. So scalars are invariant to coordinate transformation. A prime is equal to a. All right. So if phi is a certain scalar quantity in unprimed, that is xy coordinate system, if phi prime is the same physical quantity you measured from your prime coordinate x prime y prime, you will find that in both the coordinates the value of phi will be same. In both the coordinates the value of phi will be same. That is, phi prime is equal to phi. All right. So you should remember that scalars are invariant to coordinate transformation. Now let us look at another physical quantity called vectors. So vectors. Yeah, we know that like vectors are, by definition, we are already familiar with the definition, those physical quantities which are having both magnitude and direction. Right. So let us look at this problem here. Sorry, inadvertently I moved the pages. So let's say we have a vector quantity called p vector here in this x sorry, there's a typing mistake. In this xy coordinate, let's say we have a vector quantity p vector, and we can measure the same vector in prime coordinates, x prime, y prime coordinates, and we call that vector we measure in the prime coordinates as p prime. Okay, we call that p prime. So we know that p vector in x, y coordinates you can resolve into two components. What are the components you can resolve to? If you drop a perpendicular to this, x coordinate here, this is your p1. Okay, p1 or p1 I cap is a unit vector along this. And if you look at this quantity here, this vector component, this will be your p2 j cap. So you can resolve this p vector into two components: component along the I cap direction in the unprime coordinate, component along the j cap direction in the prime coordinate p2 j cap. So therefore you can write your vector as p vector has two components. One component is p component along I cap direction, component along j cap direction, p2 j cap direction. Right. Now you measure the same physical quantity here in these prime coordinates. In these prime coordinates, you can drop a perpendicular here. You drop a perpendicular here on this prime x component, and let's say this is 90 degree. So your p prime will have two component along this. Let's say your unit vector along this is I prime cap. Unit vector along y prime is, let's say, j prime cap. So component along this I prime cap is p1 prime. We call this p1 prime, and this component along this direction is, we call it p2 prime, j prime cap. So you can resolve into two components again. Okay, so vector quantity, like we are talking about, for example, this could be any vector. Okay, it could be a velocity or it could be a position vector. Any vector quantity in general, we can represent it like this. This vector quantity we can represent as we measure from our xy coordinate. This is the vector quantity in terms of components along I prime and x prime. If you measure from your x prime, y prime coordinate, the same vector, if you measure from your x prime, y prime coordinate, it will have two components, p1 prime component along your I prime component. J prime cap component will be p2 prime. Now you can write a relation between p1 prime and p1 and p2 prime in terms of p1 and p2. So how do you write your p1 prime? So I think you can see from here. Sorry, it's so difficult to give a lecture on the computer screen. Usually it's quite easy to skip the pages. So if you look at this, this is your p1 prime. From this to this is your p1 prime. In the prime coordinate, this is p1 prime is this. Okay. Now if you want to express your p1 prime in terms of p1 and p2, how will you write? Now this from this point, if you drop a perpendicular here like this, from this point, if you drop a perpendicular here, let us assume that this is 90 degree. Then what will be this length? This length will be like the previous calculation. This length will be, this is your p1, means this to this is your p1. So this length will be, in terms of this theta here, p1 sine theta. Yeah. And what will be this length from here to here, here to here. Here to here, what will be this length? This length will be your P1 cos theta. Okay. Now, this is your, so it's a little bit messy here. This is your P2 here. Like, let me trace it again. This is your P2. So this is your P2. So what will be this? This to this, between this to this will be, if this angle is theta, you remember that. So this to this will be P2 sine theta. So if you look at this picture here, if you look at the, like, if you consider the same geometry calculation here, you will find that P1 prime is equal to P1 cos theta plus P2 sine theta. P2 sine theta. And also you can write your P2 prime. If you look at this geometry again, if you do the calculation like I explained here, like we already explained in this coordinate transformation, if you do the geometry, if you work out the geometry here, you have to work out the geometry in order to understand it. If you work out the geometry here, you will find that P2 prime is minus of P1 sine theta plus P2 cos theta. If you work out the geometry calculation here, like I explained before, so I have written it a little bit quite messy. Anyway, if you work out the geometry properly on your pen and paper, this is what the relation between the two, like the components of the velocity. So if P is a vector quantity, these are the components of P in the xy coordinate. These are the components of P prime in the x prime y prime coordinate. These are the components of velocity, the same velocity you measured in the prime coordinates, that is P1 prime, P2 prime. So the components of the vector quantity you measure in the prime coordinates will be related to the components of the vector quantity you measured in the unprime coordinate using these two set of relations. So these are the two set of relations. Okay. P1 prime is equal to P1 cos theta. As I said, you can work out from this geometry here. You just let me redraw it just to clarify my point here. So you can measure a velocity P vector here. So this will be your P1 and this will be your P2. Now you have another coordinate system, x prime, y prime coordinate system. You have, let's say this coordinate system is rotated at 90 degree. If you draw a perpendicular from this to this like this, you can work out. Okay, so this length will be your P1 cos theta, and this height will be P1 sine theta. Likewise, this between these two will be your P2 sine theta, because this will be your theta here, and this to this length will be your P2 cos theta. So if you work out the geometry here, you will find that the components of the velocity, the components of the vector quantity in the components of velocity or other vector quantities in prime coordinates will be related with the components in the unprime coordinates P1, P2. P2 prime will be related with P1, P2 like this. So if you combine using the same calculation, the same steps we discussed before, you can represent this as, in terms of indices, you can represent this as Pi prime is equal to summation j equal to 1 to 2 Aij Pi, Pj. That is, if I equal to 1, then this is simply p1 prime, and we now have summation j equal to 1 to 2, I is 1, j pj. Now j is summing from 1 to 2 means a1 j equal to 1, j equal to 1 p1 plus, there's a summation here, plus a is still 1 here, j is now 2 p2. So similar to that, if you take I as 2, then your p2 prime will be, put I equal to 2 here, it will be p2 prime, then summation j equal to 1 to 2, a I is 2, j pj. So if you sum that, you will get the same set of this thing relations, and you can, like in the previous calculation, you can see that your aij is, your aij, like we did before, it is del x I prime upon del xj. Okay, your aij will be del x I prime upon del xj, just like we discussed here. Okay, we have already discussed that aij is equal to del xi prime upon del xj, and like if you follow the previous coordinate transformation relation. So what I mean to convince you, what I'm trying to convince you here is that if you have a vector quantity like velocity here, p represented as p vector here, in the unprimed coordinate, xy coordinate, these are the components p1, p2. The same physical quantity, velocity, can be measured from your prime coordinates. Then the velocity as we measure in the prime coordinates, can be represented with their components like p1 prime, p2 prime. And here we find that the components of the velocity in prime coordinates are related to the components of velocity in the unprimed coordinates by this. So this set of relations, like in the previous calculation, we can represent it like this, and like in the previous calculation just few minutes ago, you can write aij as del x I prime upon del xj. So the components of velocity, a vector quantity, now follows this transformation relation. This is called the transformation relation between the components of, this is called the transformation relation between the components of velocity in primed and unprimed. Transformation relation between the components of velocity in primed and unprimed. Here we see that the transformation in this transformation relation, the coefficient of transformation is del xi prime upon del xj. The coefficient of transformation relation is del xi prime upon del xj. So yeah, try to remember this particular transformation coefficient. Now let us look into this general Cartesian transformation relation. We can have actually, so far we have talked about two-dimensional system only. Two-dimensional system only means the index j is running from 1 to 2. So as I said, x1 is equal to x, x2 is equal to y, and x1 prime is equal to x prime, x2 prime is equal to y prime. So two-dimensional system only. You can in fact consider any n-dimensional space. That is, your index I index runs from 1 to n. Your j index also correspondingly runs from 1 to n. So if xi and xi prime are the coordinate systems in this n-dimensional space, the coordinate values in n-dimensional space, and from the transformation relation we can express like this. Here we see that xi can be, here let me go back, I think this will clarify. This we write it as our xi, x1 prime. So our xi or x1 prime can be written as a function of x and y. And this is what? Our x2 prime can be written as a function of x2 prime can be expressed in terms of x and y, means x2 prime is simply a function of x and y. Okay, so like that, you can see that the coordinate variables in the prime coordinate xi prime can be expressed as a function of coordinate variables in unprimed, and vice versa. The coordinate variable in unprimed coordinate can be expressed as functions of coordinate function of coordinate variable in primed coordinates, coordinate variables in prime coordinates. Okay, and we just found out that if I have this two-dimensional, j summation is up to 2 only, but if I have n-dimensional, the coordinate variables in primed and the coordinate variables in unprimed, they will be related using this transformation relation with a summation j running from 1 to n. If I have n-dimensional space, j summation will run from 1 to n. And also we just observed that if pi and pi and pi prime are the components of velocity or vector quantity in primed and unprimed, they will be related with by this transformation relation. So they will be related with this transformation relation. Now, in each of these transformation relation we discussed so far, the transformation coefficient is partial derivatives. The transformation coefficient, as you see, it is partial derivatives. So the xi prime, the prime coordinate variable, is in numerator of this partial derivative, and xj, that is in denominator. Okay, xr del xi prime upon del xj, del xi prime upon del xj. This is the transformation coefficient. This is the transformation coefficient. Okay, so remember that. Now this is where I would like to stop, but before I stop, I would like to discuss this gradient of a scalar. Gradient of a scalar. Then I think I can stop, or otherwise I think I should better stop here. It's almost 1 hour. I don't want to take a very long class. So I will upload this video. I will stop here, and please go through my notes. Everything is there in my notes. Please go through it and try to work out the geometry as I discuss here. And yeah, in the next class we will talk about this gradient transformation, and then we can move on to concept of convariant and contravariant tensors. So let me stop here. Yeah, you can exit the meeting. Okay.